Hi everyone. I'm going to talk about some of our recent work on prior free dynamic mechanism design with limited liability. This is joint work with Mark Braverman and Matthew Weinberg. So let's jump right into it. Dynamic mechanism design is a broad field, but one of the most fundamental problems in dynamic mechanism design is the problem of dynamic auctions. In this problem, we have an auctioneer who has one item per time step, or over the course of t time steps. And we have some bidders, in this case two bidders, Alice and Bob, who would like to buy the item. And in this example, Alice and Bob have different utilities for the different items. Alice's value for item I, the item in time step I, is A sub I, and Bob's value for the item in time step I is B sub I. And the goal of the auctioneer is to design some mechanism to decide how to allocate the item to Alice and Bob and what prices to charge them. Ideally, the auctioneer would like to design such a mechanism to, for example, maximize their revenue. So classically, dynamic auctions have been studied in the setting where A sub I and B sub I are drawn IID from some distributions, either known or unknown to the auctioneer. And there's been a lot of work in this setting towards goals like characterizing the optimal auctions. In this paper, we study a slightly different setting. We study the setting of prior free dynamic mechanism design. So in this setting, instead of A sub I and B sub I being drawn from some distributions, we allow A sub I and B sub I to be adversarially chosen sequences. And the only constraint we'll put on the A sub I and B sub I is that they're bounded in 0, 1. So although there's been some work on prior free mechanism design for a couple of mechanism design problems, we're not really aware of any prior work which studies dynamic mechanism design in this prior free environment. So you might ask, what can you even hope for in such an adversarial setting? So here are two truthful mechanisms which will serve as benchmarks for the rest of this talk. So the first mechanism, mechanism 1, we call the second price auction mechanism, and true to its name, all you do in this mechanism is you run an independent second price auction for the item in each round. So one nice feature of this mechanism is that it optimizes welfare. It assigns each item to the bidder who values it the most, and it also obtains some amount of revenue. We denote this by revenue sub SPA for second price auction, and the values is equal to sum over all rounds t of min of A sub t and B sub t, the smaller of Alice's value for the item that round and Bob's value for the item that round. The second mechanism we consider is the selling the business mechanism. In this mechanism, we again run a second price auction, but instead of running a second price auction each round, we run a single second price auction at the beginning of the protocol to auction off the entire stream of items. Now, this mechanism also obtains some revenue. We'll denote its revenue as revenue sub STB for selling the business, and its revenue is equal to the minimum of Alice's total value for all the items and Bob's total value for all the items. So one interesting thing we can note about these two mechanisms already is that in the two-bidder case, selling the business always generates more revenue than the per round second price auction. And you can see this, in particular, the min of the sums of A sub t and B sub t is always going to be larger than the sum of the mins of A sub t and B sub t. And the first term is exactly revenue sub STB, and this latter term is exactly revenue sub SPA. And in fact, this gap can be quite big. So it's easy to construct cases where a per round second price auction gives you 0 revenue, but selling the business gives you substantial revenue. For a good example of this is a case where the bidder's values are disjoint in time. So for example, the bidders value disjoint sets of items. Maybe Alice values the first half of the items or the first half of the time steps, and Bob values the items in the second half of the time steps. So from this, it looks like selling the business is a strictly better mechanism than the second price auction mechanism, but selling the business has one big drawback. It requires the bidders to pay a huge amount up front. If you'll recall, the way we implemented selling the business was the auctioneer would run a single auction at the beginning of the protocol, ask Alice to report her total value, ask Bob to report his total value, and then ask, if Alice's total value is larger, ask Alice to pay Bob's total value at the beginning of the protocol. And this requires a lot of trust on behalf of the bidders, that the auctioneer won't suddenly disappear with the huge payfall they made up front. So to account for this, we can introduce what we call a limited liability constraint. In the dynamic mechanism design literature, this might alternately be known as the per round IR constraint. And this simply says that we want to look at mechanisms where a bidder does not pay more to the auctioneer than the value they receive each round. Or in other words, the utility of each bidder each round must be non-negative. So the selling the business mechanism completely violates this constraint. And a natural question is, can we still achieve the revenue obtained by this selling the business mechanism without breaking the limited liability constraint? And this is the main question we study in our paper. So we move on to our results. The answer to the previous question is no. You can't get the full revenue of selling the business with a limited liable mechanism, but you can get a constant approximation. In particular, we show that there's a truthful limited liable mechanism for the auctioneer which achieves revenue at least 1/2e fraction of what you would get from selling the business. On the other hand, we show an upper bound showing that you can never get more than, there's no mechanism which always guarantees more than a 2/e fraction of the revenue you would get from selling the business. And 2/e is strictly less than 1, so there is a constant fraction gap between what you can get with a limited liable mechanism and what you can get by breaking this and selling the entire business at the beginning. Now, the previous result was for the special case of 2 bidders. You can ask what happens for k bidders. So it turns out it's easy to adjust our mechanism to get a 1/k times e approximation to selling the business. We also show there is a, this time not truthful limited liable mechanism for the auctioneer, but we show that this mechanism still guarantees a constant fraction of selling the business, with this constant independent of k, as long as all the bidders play undominated strategies. So as long as the strategy profile of each bidder is not dominated by any other strategy, this mechanism will guarantee a constant fraction of the revenue you would have gotten by selling the entire business at the beginning. And in the k bidder case, there still exists no truthful mechanism which achieves revenue more than 2/e times the selling the business benchmark, for the simple reason that you can embed the 2 bidder problem into the k bidder problem by adding dummy bidders. So both these results rely heavily on a subproblem we call the single bidder problem. So the single bidder problem is, you can think of it as a single bidder version of the dynamic auction problem we presented in the previous slides, but there is one significant difference. So in the single bidder version, again, we have one bidder, Alice, who has value a sub I each round, and we have an auctioneer who would like to sell an item to Alice every round. The key difference is that in this problem, we assume the auctioneer knows Alice's total value for all the items, the sum of her a sub t's, but not the individual sequence of a sub t's. So again, in this setting, if the auctioneer is allowed to break limited liability, the auctioneer could just make this offer to Alice saying, pay me v upfront, the sum of the a sub t's, and I will give you the item every round. So this achieves revenue v. The question we ask is, how much revenue can a limited liable mechanism achieve in the same setting for the same problem? And what we show is that there exists a truthful limited liable mechanism for the auctioneer which achieves revenue at least 1/e times this benchmark. And this is in fact tight. For any constant strictly greater than 1/e, there is no truthful limited liable mechanism which always guarantees that approximation ratio. Great. So I'll begin by giving a brief overview of the techniques which go into this result, and the mechanism which achieves this result. And this mechanism which achieves this result is a mechanism we call a pay-to-play mechanism. So the idea behind this mechanism is that we want to reward the buyer, in this case Alice, for her past loyalty, for buying the items in earlier rounds. So we implement this via, like we said, a pay-to-play mechanism. So such a mechanism is parameterized by a function f of x, which maps the unit interval to the unit interval. And the idea behind this mechanism is that in round t, we will allocate the item to the bidder with some probability which depends on how much they've paid so far. And in particular, if the buyer has paid the auctioneer v sub t thus far, the auctioneer will allocate the item to the buyer with probability exactly f of v sub t over v. So in general, you want this function f to be increasing to encourage the buyer to pay the auctioneer more and more. And you can compute what the optimal pay-to-play mechanism is. It turns out the revenue optimal choice of f is this function f of x equals min of e to the ex minus 1 and 1. And this leads to extracting a 1/e fraction of the total welfare v. And like I said, we can also show that this 1/e fraction is tight. The proof of the upper bound is a little technical, but the main idea, the main novelty is perhaps we show how to parameterize any mechanism not by what it does in round t, but by what it does based on how much value the bidder has seen so far. So, for example, if the bidder has gone through v over 2 of their values so far, we look at what the mechanism will do then. And it turns out we can parameterize any mechanism in this form and interpret any mechanism as a pay-to-play mechanism. And this lets us prove this 1 over e upper band. Great, so this works for the single bidder case. What do we do for the multiple bidder case? So it turns out we can reduce the single bidder case to the multiple bidder case via fairly simple reduction. So the mechanism for 2 bidders is as follows. So what we'll do is we'll begin by asking Alice for her total value, capital A, and Bob for his total value, capital B. And then what we'll do in round T, if Alice has paid A sub T thus far, and Bob has paid B sub T thus far, we'll allocate the item to Alice with probability half times f of A sub T over half of B, and to Bob with probability half times f of B sub T over half of A. And these formulas might be a bit hard to parse, but you should interpret them as follows. What we do is every round we split the item in half. We sell 1/2 of the item to Alice using the single bidder mechanism, but assuming that Alice's total value is Bob's total value. And then we sell the other half to Bob using the single bidder mechanism, but again assuming that Bob's total value is actually Alice's total value. Switching this is important to make it incentive compatible for them to report their true total values. But this also allows us to directly reduce this mechanism to the analysis of the single bidder mechanism, and we can show pretty easily that this gives revenue at least half of what you would get from the single bidder mechanism, which is 1 over 2e approximation to the selling of the business benchmark. And via similar logic, you can show an upper bound of 2 over e. In particular, if you had a mechanism which had a better competitive ratio than 2 over e, you could convert that mechanism into a mechanism with a better than 1 over e competitive ratio for the one bidder case, which we know does not exist. So before we continue, I want to present some notes on the mechanism I just described, which will hopefully convince you that this mechanism is actually a bit more robust than it might seem at first. So the first thing I want to talk about is what exactly Alice and Bob know about their sequence of values. So in general, in the prior free setting, we assume that Alice knows her full trajectory of values, in other words, all the values A sub t, and we assume that Bob knows all his values, all the values B sub t. But to actually implement this mechanism, it's still possible to implement this mechanism in a truthful way as long as Alice just knows her total value per round, the sum of all the A sub t's, and as long as Bob knows his total value per round, the sum of the B sub t's. It turns out that this is all the information Alice and Bob require in order to participate in the mechanism in a truthful way. Secondly, it's actually fine if Alice and Bob don't even know their average value per round exactly, but just know lower bounds on their total average value per round. And in this case, the guarantees we get will be slightly different. Instead of the second price, instead of the selling the business benchmark, instead of like the minimum of the 2 total values, will be competitive with the minimum of the 2 lower bounds. But otherwise, everything is the same, and the mechanism is still incentive compatible, and the mechanism still works exactly as described. Okay, the next thing I want to talk about is this limited liability assumption. So this 1 over e approximation assumes that Alice and Bob are both limited liable, that they will never bid more than their value per round, or they will never pay more than their value per round. And you can ask what happens if Alice or Bob are not subject to this constraint, if Alice and Bob are allowed to pay more than their value per round. It turns out this actually only helps the auctioneer for this mechanism. It turns out that it's in Alice or Bob's interest to just pay more at the beginning, and the auctioneer will get, at worst, the same competitive ratio of 1 over e. And finally, the previous mechanism was presented for the case of 2 bidders. You can do the exact same type of strategy to get a 1 over ke approximation for k bidders. The idea is that instead of splitting the item into 2 parts, you split it into k pieces of size 1 over k. And then again, you ask each bidder for their total value, and then you run the the single bidder mechanism for each bidder, but with the highest other value. So if you're running it for the bidder with the highest reported value, you run with the second highest value. For all other bidders, you run it with the highest total value reported to you. And this gives you a 1 over ke approximation. But like we mentioned earlier, we can do a little bit better modulo certain relaxations. So in this final slide, I want to give a high-level overview of our constant approximation factor mechanism for multiple bidders. So to refresh your memory, this is a mechanism which gets a constant factor approximation. The constant is independent of k, of the selling the business benchmark for selling to k bidders. But it has the caveat that, unlike the previous mechanisms I described, this mechanism is not truthful. Instead, it has the property that as long as each bidder bids according to undominated strategy, we guarantee that in equilibrium, we will receive at least a constant independent of k fraction of the selling business benchmark. So I won't go over the full mechanism because there's a lot of thorny details of this mechanism, but I will describe the high-level idea behind this mechanism. So to understand this, what's the problem with the previous mechanism I described where we divide the item into k parts? Well, one problem with this is that we reserve an equal fraction of the item for each of the k bidders, even though some bidders are inherently a lot more valuable than others. You can imagine a setting where the vast majority of the bidders have value 0 for the item every round, but we're still reserving 1/k of the item for each of these bidders, even if we don't end up allocating it to these bidders. So the solution we have is we dynamically adjust the share of the item allocated to each bidder by making them compete for it in a first price auction. So at a very high level, the mechanism works as follows. First, we find the second highest total value. This is exactly the selling business benchmark. Then each round, we split the item into two halves. One half we call the allocation half, and one half we call the auction half. We allocate the auction half via a first price auction amongst all the k bidders. We end this auction half once it's generated enough revenue that we've achieved a constant fraction of the benchmark. But even if it hasn't ended, regardless, in order to incentivize people to participate in this auction, we allocate the allocation half as follows. If the bidder I has paid V sub I so far in the first price auction, we allocate the allocation half of the item to the bidder with some probability which is proportional to V sub I. So this is reminiscent perhaps of our pay-to-play mechanisms. And how you should interpret this mechanism is that bidders are really buying shares of the item, future shares of the item in the auction half. So every $5 they spend in the auction half corresponds to $5 over something shares of the item for the future rounds of the protocol. So that's all I want to talk about today. Thanks for listening. On the slide, I've listed some interesting open problems related to our work if you're interested. And please feel free to contact me or read the paper for more information. Thank you.